Welcome to Lab 4, Oscillations. There are four main parts in this lab. 1. Extract motion data from a spring mass setup in which the mass swings in an arc while oscillating on a spring. 2. Employ Newton's second law of motion to build a computer model that predicts the motion of the mass. 3. Build the computer model in such a way as to show that the energy principle is satisfied. 4. Conclude by comparing the motion predicted by the model with the observed data taken from Tracker and show that the energy principle is satisfied. The data taken from Tracker is stored in a CSV file so that later we can compare our computer model to the observed motion. But we need to use some of the observed data to initialize variables in our computer model. We need the start time, t = 0, and we need the stop time so that we know when to terminate the while loop. And we need to initialize the stop time so the computer program knows when to terminate the while loop. We also need the x and y coordinates for the starting position of the mass. And since the mass starts out at rest, we can initialize its initial velocity to be the zero vector. Newton's second law allows us to predict a future velocity from a current velocity. We can then use this new velocity to predict a new position. But for this to work, we must first have initialized delta t, and we need the weight of the mass, which is 0.402 kilograms. But crucially, we need to know the net force. And in order to do that, we need to define our system. Choosing the mass as the system, there are only two significant interactions with the surroundings: the weight force, Fg, and the spring force, Fs. The net force is the sum of these. The weight force is directed down towards the Earth, so we have negative j hat in the formula. We've already initialized the mass and the constant g. This vector quantity is assigned to the fgrav variable in the Python code. The spring force is calculated using Hooke's law. The variables in this formula need to be initialized before the while loop starts and then updated inside the loop because, unlike the weight force, which remains constant, the spring force changes with each iteration of the loop. K is the spring's stiffness and LO is the relaxed length of the spring. These two variables were calculated from observational data in a recent lecture video. The spring used is the same spring used in this lab, so those values can be used to initialize these variables. L is the vector that goes from the ball to the spring attachment point. L hat is simply the unit vector for L, and S is the difference of the spring's current length and the relaxed length. It is important to emphasize that these three lines of code are updated within each iteration of the loop. All these values are used, along with Hooke's law, to update the spring force with each iteration. Now for part 3. When we worked on the computer model to predict motion in part 2, it was more convenient to use the mass alone as the system. But now, in determining if the energy principle is satisfied, we consider the system to also include the spring and the Earth. If the energy principle is satisfied, then delta E equals delta K plus delta US plus delta UG, where delta E is the change in the total system energy, delta K is the change in kinetic energy of the mass, delta US is the change in spring potential energy, and delta UG is the change in gravitational potential energy. And since there are no significant interactions with the surroundings, delta E should equal 0. Prior to the start of the loop, the formulas for kinetic energy, gravitational potential energy, and spring potential energy are used to initialize the variables K, UG, and US respectively. Note that these variable names do not start with delta. The changes in these system energies are calculated inside the loop. The variables Ki, UGI, and USI are initialized at the beginning of each loop so that when new values of K, UG, and US are calculated later in the loop, we can also calculate delta K, delta UG, and delta US for each iteration of the loop. When we run the program, we will be able to see these energy changes in a graph. Running our program and looking at part of the output, the graph shows in blue the motion predicted by our computer model. The red line shows the observed data from Tracker. The model does a pretty good job of predicting the motion. The other part of the output is a graph of the energy changes. Delta E is the yellow line that runs along the x-axis, where the change in energy is constant and 0. The energy principle is satisfied. The oscillation period is simply the time the mass takes to complete one cycle. The easiest way to determine this is to look at the time between minimum values. This works for both x versus time and y versus time. Tracker screen captures are shown here. Having identified the minimums for both x and y from the Tracker graphs, I was able to find those x and y values in a spreadsheet where I had stored the data. The X minimums are highlighted in green, and the Y minimums are highlighted in yellow. I pasted the time values for those rows into a separate part of the spreadsheet to calculate the time between them. I took averages for both X and Y, obtaining an oscillation period of 1.63 seconds for X and an oscillation period of 1.52 seconds for Y. Thank you for listening to my lab report.